Okay, I guess let's start the lecture today. So for this semester, so far we have been focusing mostly on the tabular setting, where we have finite number of states and number of actions. So in the next 2 weeks, we will advance to a new topic, which we deal with a large number of states and large number of actions. So typically, it's a large number of states. So we will deal with the new topic, that is reinforcement learning in large state space. Okay, so by large state space, the methods we're going to do is called function approximation. So we'll introduce what are those things later. So in this week and the next week, we will basically dealing with this topic. So we will divide it into 3 parts. First, today we will do some overview on what are the challenges in this large state space and what are the basic methodology for function approximation. And then we will deal with a simple case. We will do the linear function approximation. Okay, because basically everything will, as we do in theory, we'll start everything from the easier case, where easier case essentially we will approximate value or policy by linear functions. And after we study the linear function approximation, then we will talk about the general function approximation. Essentially generalize what we learned, the principle under this linear function approximation to a generalized version. And this will be topic of the next week. Okay. So let's start with the overview then. So we will talk about what do we mean by reinforcement learning with a function approximation. So let's just recall that we have been talking about tabular MDP so far for this semester. And if you still remember, one thing very important we discussed in this class is called sample complexity. So the sample complexity for learning tabular MDP is something like the following. That is poly H, where H is the horizon of MDP, and S is number of states, A is number of action, over epsilon square. This is number of samples we learn the tabular MDP, either in generator model like simulator setting, or in the online setting, or in the offline setting where we pay this concentrability coefficients. I think the most important thing is this is linear in S. But as just we said, in a lot of practical scenarios, we want to deal with this large state space. And a lot of practical applications, this number of states is really tremendous. Let's just first think of example where in 3 or 5 years ago, a very famous paper on reinforcement learning is basically they first knows how to use deep neural networks with reinforcement learning to solve a very simple Atari games, but with 50 different Atari games. So each Atari games, the number of states is essentially corresponds to each different states. Okay, so we can talk about what is the roughly number of states in Atari games. So basically, each different states corresponds to different pixel values. In the image. Okay. For those games, this is like a video game. So it's each different where we have like around 200 different pixels in each image, and each pixel has also about like 200 different values. So this gives a tremendous different possible numbers of states. Basically, if we're paying something linear in S, we're kind of like screwed. Like no algorithm in practice can pay something linear in S. So we cannot afford linear in states. Samples.
When you say learning tabular MDP is this is the complexity for basically any all settings and all algorithms. It has some sort of LHSA over it.
Most algorithm, if you're doing like a too terrible, like algorithm is like too bad, then you won't do this. Yeah. But in this class, we talk about value iteration and some variant of value iteration, also Q-learning. They all have like this type of guarantees. You're right. Okay, so first we notice the number of states is like really, really large in those kind of applications, so you cannot really afford anything like linear in S, number of samples. Second thing you observe is in practice, we may never visit the exact same state twice. Such a thing as like in the robotics, where essentially you can think the state is represented by some real value, like in terms of position, in terms of joint angles, something like that. And if it's a real value, it's very difficult to basically experience the exactly same real value like the twice. Okay. So in this kind of scenario, this is also related to our old strategy in tabular MDP, basically in this simulator setting. We just try other states. And in exploration setting, we're essentially doing similar stuff, where we basically look at different states. If some state is rarely visited, we'll just try to visit that states. But here it's kind of like saying it's just not possible to visit other states. So the same strategy would not work. Okay, so this kind of all hints to, in the like large state space scenario, we need some new mechanism which we haven't been talking so far in the tabular MDP. That is so-called generalization. Okay, so this is a new thing in the function approximation. By generalization, we want to learn the generalization. There are a lot of different generalizations in the learning scenario, like in terms of overfitting or that kind of generalization, or out of distributed generalization. Here, we're specifically talking about generalization where we want to generalize from the observed states. Okay, this is something we have seen so far in the data, or we have explored, we have played in our data, but we want to generalize the stuff we learn from the observed states to unobserved states. Okay, so this is what we really want to deal with. And of course, there's like no free lunch. In terms of the way we can generalize from observed states to unobserved states, basically we need to encode some similarity measure between those states. Only if we assume, like with some prior knowledge, we know states are similar in some specific way. For example, we know like in playing Atari games, if certain 1 or 2 pixels change by some small values, those images should be very similar. In that kind of scenario, basically, we can encode some of our prior knowledge so that we can talk about what states are similar, and we can do this generalization. Okay. So the key here, key to this generalization is we need to encode similarity structure between states or among states. So once we have some prior knowledge about similarity, we can generalize from observed states to unobserved one. So this leads to basically the main approach, how we're going to handle this large state space scenario. So the approach is called function approximation. So in a high level, a very simple way to encode such a similarity structure is basically parameterize either models, values, or policies by specific class of functions. Okay. So this is why this is called a function approximation, because we no longer as a tabular setting, we essentially remember the value for all the different states and remember the model for all different state action pairs. Where here, we no longer do that kind of table approach. We just parameterize everything by some function so that they have some implicit constraints within those different states. Okay. So several approaches we already mentioned there. One thing we can do is we can parameterize models. In terms of we use neural networks to parameterize transition probability, which is P S prime given SA. And in tabular setting, we essentially remember this entire transition probability as a table. But here we're saying we have to parameterize by some neural network parameter, theta. Okay, those are the model parameters. These are function parameters. We can also say we're going to learn the reward, which is also a function of SA and theta, where theta is, again, the function parameters. Second approach is we're going to approximate the value function, which actually in this class, we will talk a lot about this approach. In terms of approximate value functions, we will approximate the Q value, QSA, by some functions, neural networks with parameter theta. And the third approach is we can also parameterize policies. That is, we will essentially parameterize this pi function, A given S, by some parameter theta. And some last approach where, in practice, people also do this algorithm called actor critique. Essentially, parameterize both value and policy. And the actor critique method is essentially we will fix the value and you learn the policy by this approximation. And then you fix the policy and then you learn the value by approximation. Essentially, you learn them alternatively. So we know the key of function approximation essentially is we restrict model, value, and policy. To be certain specific parametric form. For example, we restrict the value to be linear function, we restrict the value to be polynomial, we restrict the value to be like a two-layer neural networks, something like that. And by this restriction, we really encode this similarity structure within those state. Okay, this restriction essentially we kind of encode the similarity structure, and after we do this restriction, we will learn the parameter theta. So eventually, we no longer learn a table of value, table of like policy. We just learn this parameter theta. And after we learn a function, for example, after we learn a model, we can directly do planning and we get the optimal policy. After we get the Q value, we can also directly implement the greedy policy. We also get the optimal policy. And that policy is kind of like the same thing. Okay, any questions so far about this like function approximation approach? If not, we will basically iterate a little bit about the challenge in this large state space scenario. So we need to first understand what are those challenges, and then later we kind of handle those challenges in theory. Like either say some challenge is too difficult, we like postpone it, we deal with it later, or we kind of we directly face those challenges. I think as I summarize, there are a bunch of challenges. I think the first challenge we already mentioned is we call it like sparsity. Sparsity basically says there are a lot of states that are not observed. And in fact, for robotics or for like when you want to play Atari games, the number of states you visited is actually very, very small. Most of states are not observed. So the sparsity essentially is equivalent to like, the challenge of sparsity is essentially require our algorithm to handle this generalization. We want to generalize from observed states to unobserved states. And the function approximation by itself also introduces a new challenge that is called misspecification. Okay. That is basically by dealing with function approximation, that is we say we will approximate, for example, Q value by this neural networks with some parameter theta. But in reality, we also have an optimal Q value function, Q star SA. This can also be defined for even like infinite number of states, MDP. So this optimal value may not be able to be parameterized by theta. Or we can just fastly say the Q star, this optimal value function, may not in our function class F. Okay, this is like a function class of F. Basically, the function class contain all the function can be represented by this theta. Like for example, all two-layer neural networks or all linear function. So in that kind of scenario, if the optimal value is not a linear function, but if we approximate the optimal value by linear function, then we kind of introduce this arrow, this so-called misspecification. And this will definitely hurt our performance. Okay. And in the third, we also talk about in the online scenario, we also need to handle exploration versus exploitation on top of all the sparsity and misspecification. Okay, and there are also more challenges, I think. So in this class, we will basically handle those challenges, and specifically mystification is like very difficult to handle and require a lot of like new advanced, either require a lot of new advanced techniques, or there are a lot of like hardness result. So in this 2 weeks, in this lecture, we will basically dealing with, we'll use the approach of a value function approximation first. Just because this is like also one of the most practical approach, which we just directly parameterize value. And we will dealing with this function approximation without misspecification. So we will handle a simpler setting where to avoid some like a very difficult scenario. So we will only handle the sparsity and exploration challenge. Okay. So this is essentially the roadmap of what we will do in the next 3 or 4 lectures. Value function approximation, and we handle with sparsity and exploration. Okay. So this is essentially our overview. Any questions so far? If no questions, we will directly jump into this topic. We will start with a simplest setting, where we will first talk about the linear function approximation. Since we already mentioned, we will restrict our attention to this value function approximation. So in this sense, we're essentially saying we're going to approximate Q value by a linear function. So more formally, what we're talking about is we assume we know a feature map. Okay? We assume this is like given. Okay? The agent is knowing a feature map. This map is we denote it as a psi, phi, and this map is a map from a state action pair to a d-dimensional vector. So this is like a feature map. Essentially encodes a state action by a d-dimensional vector. Okay. So we say phi SA is the d-dimensional feature of this state action pair, SA pair. So in general, you may ask like, how are we gonna know this feature? So of course, like in a lot of practical scenario, this feature, like you either need to learn it or some engineer like hard code design the feature. For example, if you want to design some reinforcement learning for playing Tetris, like you can look at how many holes you have and what are the next what are the index number of the next pieces. And in practice, people realize if you just use like those handily code, like hard-coded features as some linear feature, and you learn some linear value on top of that, and they receive like quite good performance. So for some simple scenarios, you can actually just hard code the features, and they will actually perform reasonably well. So once we have this feature map, we can essentially do the following parameterization. That we will essentially parameterize all the Q value by a weight vector W. Okay, this is a weight vector. And this essentially is the parameter theta we're talking about earlier. This is parameter we need to learn. And we can essentially parameterize all the Q value by W transpose this phi SA. Since this feature map phi is we know in advance, or some other people already give it to me, all we need to learn is this W. So we know in general, if we simply approximate the Q value by this linear function, like in a general scenario, we know there's a misspecification. So in general, like Q star needs not to be linear. This will introduce a lot of misspecification, which just turns out to be very challenging. So for quite a long time, we kind of struggle even in this like a simplest scenario, where it's like linear function approximation. We don't really know like what kind of guarantees we can talk about, what kind of algorithm and what kind of positive result we can talk about for this kind of thing. And it turns out like when we have a misspecification, it's always very easy to give the hardness result, saying like something is very difficult to learn, or some in worst case, like we don't have any algorithm able to learn this. So one thing as a first step to understand like linear function approximation, under what kind of scenario this approximation would work, is to give a strong sufficient condition so that we can say doing linear function approximation is reasonable. So in this kind of scenario, we will essentially, as a first step, as we said in this class, our approach is we want to rule out the mystification. Essentially, what we're saying is if a generic case is like too hard, let's understand the easier case first. Okay, we will understand the well-specified setting first. Well-specified setting means under certain assumptions, we will actually make sure the Q value, Q star, is actually linear. Okay? well-specified setting in this kind of scenario is indeed Q star is linear. So the question is, what kind of condition will actually guarantee us the Q star is linear? So it turns out there's a set of simple conditions that will make sure the Q star is linear so that we can learn something reasonable. Okay. The setting we studied recently is called linear MDP. So we'll introduce linear MDP and show why it will guarantee the Q star is linear. Yes? Question? Yeah, linear in the non-phi feature.
But phi could be like a nonlinear.
Phi could be a nonlinear map, yes. Phi could be arbitrary things. It can be some neural networks or something. But basically here we call it linear because we don't handle the complexity of learning this phi feature. We basically assume this is like given already. Yeah, very good question, thank you. Yeah, by linear we always mean like everything is like linear in this feature map phi. Okay. So formally, what do we mean by linear MDP? Linear MDP is, of course, a special case of MDP. So when we talk about MDP, we always have the following elements, that is set of states, set of action, and reward function, transition, and also the horizon. So here, the S is the set of states. Only thing different from the tabular setting is in this case, we even allow this S to have infinite cardinality. Okay. For simplicity, we just only handle the finite, infinite number of states. We still restrict our action to be finite. Okay. So the key thing in linear MDP is in how we assume the reward and the transition, how reward and transition will come from. So in the linear MDP, essentially by its name, we essentially just say that we require both reward and the transition to be linear. In the following sense, that the reward need to be parameterized by this theta h, transition, phi SA. Okay. And this is the parameter. Essentially, linear MDP assume reward by itself is a linear function of this feature map phi. And also the transition. Here we write it in the measure theory language. Is the transition of starting from SA, state action pair SA, to the next states, is the inner product of a d-dimensional feature, phi SA, times a d-dimensional measure, mu, the vector version of mu, dot. So this is like a d-dimensional measure. We will talk a little bit more about this notation. So by d-dimensional measure, we really just means each dimension is a probability measure. Measure essentially some like a generalized language for probability. For simplicity, you can just think of measure in terms of this dot. You can put any like measurable set, because in general, like states can be continuous. So for example, if we have some set A is a subset of all possible next states. Let's just say this A is a set of possible next states, or like a subset of possible next states. Then this pH A given SA just means a condition on starting from SA. What is the probability of the next states lands in this subset A? Okay. Of S prime in A if starting from SA. And by this condition, essentially it says this is equal to some phi of SA and times some common measure mu this and times A. Okay, so in this sense, this is a linear. So this is saying both reward and transition are linear. We use this measure theory kind of notation because we want to essentially unify the things of both discrete probability measure, also the like general like continuous probability measure, or like even some mix, like some part is discrete, some part is continuous. So we can always like use this same language, like the measure theory. But in principle, it just means that transition probability is also linear.
So
yes.
Is it equivalent to say Q star is linear and reward and transition are linear, or is reward and transition being linear only one way to make Q star?
The second one. So the true answer is actually this is like assuming linear MDP is the sufficient condition to say Q star is Q star is linear. But Q star is linear, you can also use some other ways to make sure.
But we just studied that.
Yeah, we just studied this like simple case. Yeah, as we said, this is like one of the sufficient conditions. We actually prove later, like this will allows this to be true. Okay. So after introduce this linear MDP, this looks like a set of like abstract conditions. So we will first connect this new notion linear MDP to the existing one's tabular setting, and we will also look at some new examples which we cannot cover by tabular setting. So the first example is tabular MDP. So we will actually see the tabular MDP is a special case of a linear MDP. So in that case, we just need to specify in the tabular MDP what are the linear map phi and what are like why the reward and the transition satisfy this linear form. Okay. So in the tabular MDP, we know the states, the set of states is the number of states is the cardinality of S, like this curly S. And the number of action A is the set of the cardinality of action A set are finite, both finite. So what we will do is we will set the dimensionality of the feature map equal to the number of states times the number of actions. This is the dimensionality we constructed for tabular MDP. And the phi SA, the linear map we constructed for the tabular MDP, is just the like unit vector in each dimension, and the dimension is like encoded by SA. Okay, so this SA kind of encode a coordinate, because we have like SA dimensionality. So each state action pair like indicates one of the coordinate in one of the dimension. So this is like an indicator vector that essentially says only SA coordinate is 1. All other coordinates are 0. So what remains is we just need to specify what are the theta and mu's so that we can essentially cast tabular MDP to be a special case of linear MDP. Okay. So what we will do is then set theta h and mu h so that ESA transpose theta h is equal to RHSA. Okay. This equation kind of like says for what are the values of each coordinate of this theta vector. Theta again is a vector in like SA dimension. It's an SA dimensional vector. This essentially says the one coordinate of the theta is equal to blah blah. So this fully determines theta. Similarly, we also need to set the E transpose SA mu h dot. This is equal to PH dot SA. Okay. This also, again, this is like a SA dimensional measure. And by doing the projection onto this little SA coordinate, this essentially just says one-dimensional measure is just a one measure. And this is like saying one coordinate of this d-dimensional measure is precisely equal to this measure. This also fully determines mu. So by doing though, we have cast this tabular MDP in the form of linear MDP. And this directly implies that tabular MDP is a special case of linear MDP. So the first case is really straightforward. But also, in some sense, it's not very interesting. If the linear MDP can only handle the tabular MDP, then we don't need to develop the new thing. We kind of we go back to what we have been studying for the past weeks, for the past 4 or 5 weeks. So we need to talk about some examples which can be potentially new examples beyond the tabular setting. So we talk about the second example. We allow not only the tabular setting, but we allow some simplex feature space. In a simplex feature space setting, we essentially are a lot more general. We allow, as long as this is a feature space is essentially constructed as a set of all the possible feature map phi SA for all possible SAs. Okay. So it's a collection of all the possible feature maps for any corresponding state action pair. As long as this feature space is a subset of d-dimensional simplex. Okay. By d-dimensional simplex, you probably know d-dimensional simplex is essentially says all the coordinate need to be greater than 1, and also summation need to be equal to 1. Okay, let me just. So d-dimensional vector, or d-dimensional simplex, is the set of d-dimensional vectors, x1 to xd, so that xi greater or equal to 0 for any I in D, and summation xi, I from 1 to D, equal to 1. Okay. This is d-dimensional simplex. So if we have feature space that is a subset of the d-dimensional simplex, on the other hand, if we have each coordinate of this measure is a probability measure. This is the first condition, this is the second condition. Probability measure essentially says it's not only just a measure, but if you take the whole set, it's equal to 1. So it's like a probability. So in this case, then you can check RH, PH are well defined. In a sense, given by this construction, if all the coordinate of this mu is a probability measure, and we guarantee the feature map is in the simplex, we will guarantee this is actually a probability. Okay, this is not something like crazy giving you some negative result. So in this sense, this is like well defined. And this essentially gives the other scenario where linear MDP can make sense. So in this example, we allows infinite number of states. This example doesn't really care about how many states you have. As long as you can, even if you have infinite number of states, as long as you can map those state action into some like simplex feature space, and you're ensured that reward and the transition are like linear functions of those things, and then you're in a good shape. Okay. So any questions so far about this?
What's like the interpretation of the probability simplex?
Probability simplex.
Or sorry, what's the interpretation of the simplex with dimension b? Is that?
It's kind of like just. It's kind of like just. You can think it's the one norm Bohr, like whatever vector on this set is like has a one norm equal to 1. But it also requires all the coordinates to be positive. Yeah, and turns out the one norm is like the important thing. Okay. So earlier we kind of like we mentioned we introduced this linear MDP because we essentially want to find some specific sufficient condition so that we can ensure there's no misspecification. We can ensure all the like Q star is linear. So it turns out we can even prove a stronger theorem. So we will say linear MDP actually ensures not only the optimal value function, but all value function, that is the value function of any policy. All value functions in the sense of value functions of any policy. Are linear. Okay, so this is the proposition we're going to prove now. So proposition. For linear MDP, and for any policy pi, here exists weight vector W H pi, H from 1 to capital H. Essentially, we have one weight vector for each step. So that for any SAH tuple in this set of states, set of action, and H, we have the following holds. That Q pi HSA is equal to phi SA inner product with WH pi. Okay, so this essentially says for any policy pi, there exists a set of linear weights so that this Q value is linear. Because for any policy, the Q value is linear, and of course, for the optimal policy, this is also linear. And I think we note this is like a very strong in the sense we do say this is like for any policy. We never say this is like linear policy or whatever. So you can just throw in any arbitrary weird policy that only, like even if we have a linear map, we can do some policy that only, like for example, for this state, this specific state is we're doing something completely different from all the neighborhood state or something like a very arbitrary weird policies, and this proposition still holds. So that's why the linear MDP assumption, in some sense, is also a strong assumption. Okay, so we'll do a quick proof, and this proposition is actually not hard to prove at all. Basically, what we do is by induction and by Bellman equation. We don't even need to do induction. We just directly by Bellman equation. Okay. So by Bellman equation, we always know the Q value, Q pi HSA, is still equal to R HSA plus pH, VH plus 1 pi SA. Okay. So of course, Bellman equation still holds for function approximation. Bellman equation just generically holds. Okay. So now we need to plug in what we have for reward and transition. So for reward, we know reward is a linear function of a feature map phi. So this is equal to inner product of phi SA times theta h. And for the second part, essentially we need to do an integration over this VH plus 1. So it turns out linear MDP first sample the next states, and then for next states we need to look at the value of VH plus 1 pi. So you can write out this PV of the next value is equal to, again, linear function phi SA. You can actually push the integration inside. It becomes something like a integral of VH plus 1 pi S prime d mu S prime. So we can simplify this form a little bit. That's just equal to phi SA inner product with theta h plus integral of v pi h plus 1 S prime d mu S prime. This essentially says I don't really care about what your value in the next step. It can be nonlinear, it can be arbitrary stuff. And I think most cases nonlinear. This only says like Q value is linear, but V is not necessarily linear. So in this case, I don't care about what's your value in the next step. I can basically, we know this entire thing is definitely a d-dimensional vector. Okay. We can say this is like a WH pi. And this is definitely in the d-dimensional vector. So this immediately implies Q pi is linear. So basically, it's quite quite expected because in Bellman equation, it's just the reward plus the transition to the next value. And we already assume both reward and the transition are linear, so of course the value is linear. So of course, this is like the good part of linear MDP. We essentially find a sufficient condition so that we make sure the optimal value is linear, and we actually make it stronger. Not only the optimal value is linear, arbitrary value, like the value of arbitrary policies, are linear. Of course, on the other side, the disadvantage of like making such a strong sufficient condition is the strong assumption always makes a lot of restrictions. So we will also note that linear MDP is a strong assumption. For example, it put a lot of restrictions on the feature space and something maybe we don't want. Okay. So we'll talk a little bit about the restrictions of linear MDP. We note linear MDP kind of like assumes both reward and the transition are linear. And specifically, like transition are linear means transition is like a probability. Transition cannot be some arbitrary function. So transition is linear put a lot of restrictions on the feature space that's possible, and also like what are those measures, because you need to make sure those are the valid transitions. Those are not just arbitrary functions. So we will do the second proposition. It says for linear MDP, for any SAH in the all possible state set, action set, NH, we have the following. That the feature map phi SA transpose with this mu measure hat if we take on the all possible state set. Okay, this is like the entire state set. We essentially says this need to be equal to 1 because this is a probability measure. If we kind of like we say that what's the probability of the next states lands in all state set, it's of course 1, right? Because next states has to be lands in this set. And also, we need to say this phi SA transpose of mu H, this B, let's say this set B, needs to be greater than equal to 0 for any measurable events. Subset of this S. So the proof of this is like quite straightforward. This is like immediate, basically just immediate from the requirement that the transition probability, if we say what's the probability of a transition to the whole set, that's just equal to 1. And the transition probability to any measurable set need to be non-negative. Okay, Those are just two conditions. Are the basic conditions for probability. Okay. As we said, the most important construction is we say the transition is linear, and the transition linear because transition is a probability. So this will put a lot of constraint. So first, the probability need to be sum equal to 1. And all probability need to be non-active. Those are two basic requirements for probability. Okay, and this just gives this condition, and this gives the second condition. So what does proposition say? Like why it gives a very strong condition? We kind of like notice this S is like the whole state set. So this is fixed. And the measure on this whole set is also a fixed thing. So this is like a fixed vector. But here, this is like for any possible SAH. Sorry, we have H. We should have, okay, no, we don't have H. So basically, this is kind of like saying, for any SA, this feature maps inner product with some fixed vector equal to 1. Okay, and this gives a hyperplane. This is essentially equation for hyperplane because this is a fixed vector. So it kind of like says all this feature needs to land in this hyperplane. Okay. This specific hyperplane, that is the inner product with some fixed vector is equal to 1. The projection on some direction is equal to 1. Okay, so this conclude that is the feature space must be in a hyperplane. For example, in the previous example, we say we have some simplex feature space. Simplex is a hyperplane. Okay? So that's why that one is solid. But this essentially says it requires feature map must be in a hyperplane. So for example, if you want the feature space to be L2 ball, for example, this is like a very simple choice. Sorry, you cannot do that. The linear MDP does not allow that. Okay. So it cannot be. Okay. The feature space cannot be, for instance, an L2 ball. This kind of like says linear MDP is a basic model to study linear function approximation. Linear function approximation, let's say linear FA. But it's also a strong model. Restrictive model in the sense assumption is very strong and put a lot of unwanted assumptions, put a lot of unwanted structure. For example, I think in a lot of practical scenario, really like feels like the feature space L2 ball is like very normal. But basically, once you assume you have like transition is linear, you cannot allow any like L2 ball feature space just because it violates the linear transition assumption. Okay, so after understanding the basically the advantage and disadvantage of linear MDP, the advantage is basically it's well specified, so it makes everything simple. All the Q values are linear, but the disadvantage is like put a lot of unwanted assumptions. And after we understand the pros and cons of this simple model, we goes to the interesting part. We talk about how we're gonna learn this linear MDP. Okay, although we know this like put a lot of strong assumption, but it's always not hurt to like study the simple model first to understand like for the basic model how we're gonna learn the linear MDP. So it turns out we will actually also do some algorithm similar to value iteration. But here, because we are doing function approximation, we can no longer do the precise function value iteration. So we introduce a variant of function value iteration called least squares value iteration. LSVI. So essentially, the whole idea of least square value iteration is to approximate Bellman equation using data. Recall that in a tabular setting, what we have is we do this Q hat when we have like samples instead of the real transition. What we have is this R Q hat is equal to RH SA plus P hat V hat. And this is like a empirical estimate. By counting like how many times we observe the next state as prime given the specific SA pair. What?
Isn't this only for if you have a single?
I think even for the online setting, like even for the bonus scenario, we just adding a bonus, right? Effectively, we're still doing this. Like after we collected data, we like in the exploration setting, we're doing that. In offline setting, we're also like doing that. Okay. So I think the difficult part is in the linear setting, we essentially prove if we have the true transition, this is a linear function. We can essentially approximate everything by linear precisely. But the problem is when we don't have the precise value function transition, we only have like estimate from the empirical transition, then this is not necessarily like an equal sign. It's only like approximately the linear function. It's not necessarily just exactly linear function. So in the linear MDP, basically we want to find the linear value function. Essentially, we change this equation to find the linear value function to minimize the error. So it turns out, basically, we parameterize Q hat H to be something like WH hat transpose phi SA. So how are we going to compute the WH hat phi SA? This is essentially the parameter. So we will set this parameter to be the argmin of weights, which minimize the square loss of some summation from all the data, i.e. from 1 to n, that we have W transpose phi SIAI subtract I, subtract VH plus 1 hat SI prime if we have a lot of data of those tuple. SI, AI, I, SI prime. Okay, so you can think this in the tabular setting, if this is like just like a basis vector, then we're essentially minimizing the minimizer of W is essentially solving the Q value for the table. Okay. Now the only difference is because we're in a linear scenario, so we're not necessarily going to make this equal to 0, and so we kind of just minimize this square error. Okay. So we will stop here for this lecture. In the next lecture, we'll talk more about the property of this LSVI and under what kind of scenario we can give theoretical guarantees for it. Thank you. And also the third homework will be released today.